Hello all, welcome back to Operating System course. Today let's get started with the third chapter, that is Synchronization and Deadlocks. First we will see the contents of the chapter. So we'll see synchronization, its background, the critical section management and the semaphores. Semaphores concepts only, okay? This is in the synchronization, and in the deadlocks we'll see what is a deadlock, then its system model, characteristics, methods for handling the deadlock, how to prevent deadlock, how to avoid it, how to detect it, and how to recover from a deadlock. So first let's get started with the synchronization. So what is synchronization? So the basic meaning of synchronization is the operation or the activity of two or more things that happen at the same time or same rate. Okay, so this is the basic definition, wherein the activity of two or more things that happens at the same time. So now what is synchronization in operating system? So this synchronization comes into picture when you have the process executing. Okay, so synchronization is the task of coordinating the execution of the processes in a way that no two processes can have access to the same shared data and the resources. So basically we have two types of processes, right? One is independent process, another one is cooperating process. So independent process means the process which will not affect the execution of other processes. Then we have cooperating process. Now these cooperating process are the one that affect or that will be affected by other processes that are executing in the system. So this cooperating process can either directly share a logical address space, or they'll be allowed to share the data only through files or messages. Now what do you mean by logical address space? So it is nothing but wherein your process that shares the both code and data. Okay, so that is logical address space. So this synchronization problem, it occurs in the case of your cooperating processes. Why? Because these cooperating processes, they share the resources, right? Next we will see the producer consumer problem, which is a classic example which says why we need synchronization. Okay, so in the producer consumer problem we have two processes. One is producer process, another one is the consumer process. So what is producer consumer problem is that, so producer is a process which produces an item and it keeps the item in the buffer. Okay, it keeps the item in the buffer. We have to note here that the buffer size is fixed. Okay, this buffer size is fixed. So the producer process, it produces an item and it keeps into the buffer, and your consumer process, what it does is like it consumes the item which is produced and kept in the buffer by your producer process. So say suppose your producer has produced three items, 10, 20 and 30. Now what will happen is like your consumer can consume from here. So there are few problems with this producer consumer problem. So the first one is like when the buffer is full, okay, that means remember we had a fixed buffer, right? The size is fixed. So here the size is 3. That means your producer process can produce 3 items and keep in the buffer. It cannot create fourth item and put here. Why? Because there is no space, right? So one limitation is here, producer process, it has to produce the item only when the buffer is not full. Whenever the buffer is full, it should not create any item. Fine. The next problem is that your consumer process, this process can consume from the buffer, right? But when cannot it consume? Whenever your buffer is empty, whenever there is nothing in your buffer, okay, there is no item in your buffer, your consumer process cannot consume anything. And the third problem is that the producer and the consumer, they should not access this shared buffer at the same time. So this is another problem. Okay, so next we will see the code for this producer and the consumer process, so that we'll see what is how the problem will occur in there. Okay, so this is the code for your producer and consumer process. On the left hand side, this is your producer process and this is your consumer process code. Okay, So first we'll see about the producer process. After that we'll come and see this consumer one. Okay. So first we have this condition here, right? While true. This means there is no condition. So this is always true. This while loop is always true. So that means what will happen? You will enter into the body and you'll start executing it. So first what will happen is like you produce an item and you store it in a variable called next produce. Okay, as this is a producer process, this process will produce an item and it would store it into a buffer which is of fixed size. Now next we have a condition called as while counter is equal to buffer size. First we'll check the counter value. Okay, let me take the proper example and we'll traverse this code. Okay, so let's assume that the buffer size is 5 and by default your counter and variable in would be 0. This counter variable is there, right? Here you can see this counter and here also we have counter. That means your counter variable is shared by both your producer process and your consumer process. Again your buffer will be shared by your producer as well as the consumer. Okay, so this is our buffer. Okay, you can see over here, right? And we will consider that buffer size is 5. That means your producer can produce max up to 5 items. So by default we have counter and in as 0. So in is nothing but your pointer. Okay, this pointer to the buffer. Fine. So first we'll have okay, let me give the location names 0, 1, 2, 3 and this is the fourth location. That means altogether you can store 5 items in this buffer and by default in will point to this 0th location. This is your in value. Okay, and counter is also 0. So when you enter this loop first, it will check while counter is equal to the buffer size. What is your counter value? It is 0, right? It is here, right? 0. Whether 0 is equal to 5? No. That means this condition would be executing now. So whatever the item you have produced, it should be kept in buffer of in. What is the value of in? By default it is 0, right? In buffer of 0, that means in 0th location of your buffer, you have to keep the item which has been produced. Let's assume that your producer process has produced an item called number 100. Okay, so that 100 would be stored in buffer of 0. Why? Because in is by default 0, right? So your 100 would be placed in buffer of 0. Okay, this is your producer process here. Okay, so it has produced an item 100 and it has kept in buffer of 0, that is here. Next we have in is equal to in plus 1 modulo buffer size. What is the value of in? That is 0. 0 plus 1 mod buffer size. What is the buffer size? 5. So 0 plus 1 is 1. 1 mod 5, you will get 1. Okay, so first you will have in value as 1. Previously it was 0. After performing this operation, it has become 1. And what is your counter value now? By default it was 0, right? Counter plus plus, that means counter is equal to counter plus 1. That means right now your counter value is 1 after performing this operation. So we'll go back and traverse this for the second time. Why? Because we have to traverse 5 times, right? Why? Because the buffer size is 5. Okay, next check. Now this has been updated. Okay, these values counter and in value has been updated to 1 and 1. So again we'll go back to this while loop. Okay, this while loop, this is always true. That's why I'm not saying it again and again. I'll consider from here. Now the counter value is 1. Check whether 1 is equal to 5. Is 1 equal to 5? No. That means come to this statement. Now your buffer in value is 1, right? So buffer of in the first location of your buffer, you have to put the item which has been produced. We'll assume that we have produced the item 200. Now that 200 will be kept in which location? Buffer of 1, right? So this will be replaced by 1. So in the first location of buffer, we'll put the produced item which is 200. Okay, I'll write like this. Next again perform this operation. What is the value of in? That is 1. 1 plus 1 mod buffer size is 5. So 2 mod 5. That means the value is 2. Previously it was 1, now it has become 2. The counter is also incremented, that means previously it was 1, now it has become 2. So now it is 2. Okay, we'll traverse again here. Now the counter value is updated, counter value is 2, right? Whether 2 is equal to buffer size, which is 5, 2 is equal to 5, no, right? Come here, and now we'll assume that the process has produced an item called 300. Where should that 300 has to be placed? In buffer of in. What is the value of in? The updated value, it is 2. So in the location, so buffer of 2, you have to place the value 300. So buffer of 2 is here, the value 300 would be pointing here. Note that this in is there, right? In, it points to the next location. Whenever I am saying here to in is equal to 0, 1, 2, it means this in has been moving. Okay, next we'll perform this operation. So in value is 2, 2 plus 1 is 3, 3 mod 5 is, you'll get 3. Okay, the updated value of in is 3. Counter also you incremented by 1, 2 plus 1, which is 3. Okay, again we will go back to this while loop. Check now whether counter value, that is 3, is equal to 5, which is false. Come here. Now the updated value of in is 3. So in the buffer of 3, you have to keep an item called as, say suppose 400. So in this location buffer of 3, you have to keep an item called 400. Okay, now again do this operation. The in value is updated, in value is 3, 3 plus 1 is 4, 4 mod 5 is 4. Now the updated value of in is 4. Counter value 3 plus 1 is again 4. Again go back to this while loop. Check whether 4 is equal to 5. No. Come here. So the updated value of in is 4. So in the buffer of in, say place the value 500, which is here. I'll place the value 500 here. Okay, then do this operation. In value is 4, 4 plus 1 is 5, 5 mod 5 is 5. Okay, 5 mod 5 is 5, and the counter also you incremented 4 plus 1, which is 5. Now see that the buffer has been full. Let's again go back to this while loop. Now check the value of this counter. What is the counter value? It is 5, right? Whether 5 is equal to the buffer size is 5, right? Yes, the 5 is equal to 5. That means it would be an infinite loop. Stay in the loop itself. Do not, again execute these statements. Fine. So whenever this counter is equal to buffer size, this condition has become true. Your producer process that understands that the buffer has been full and it has to wait until the consumer process, it consumes at least one item from the buffer. Why one item? Why? Because whenever the consumer process consumes at least one item, your producer process, it has one empty slot, so that empty slot can be used, and in that it can put your producer process can put an item, store an item. Remember again, this buffer is a circular buffer. Okay, that means after 4 again it comes back to 0. Fine. Now let's look into this consumer process. So we have we already know that this counter is there, right? This counter variable, it is shared between your producer process and the consumer process. That means whenever you execute this consumer process, the counter value by default would be 5. Why 5? Because the latest updated value in this producer process for the counter is 5, right? That's why the same 5. Why? Because this counter is shared, right? This value variable has been shared. That's why here counter value by default it would be 5. Let me write it. This is counter. By default it would be 5, and we will make use of another pointer variable, that is out. By default it would point to 0. In the same buffer it would point to this 0th location by default. Okay, this is out. Okay, so we will now talk about this consumer process. So first this you already know, while true what happens. Next check while the counter is equal to 0. the counter value is 5 by default, out value is counter value is 5 by default, right? So whether 5 is equal to 0, no, right, which is false. Then what is your next statement? You have to execute this one. So buffer of out is okay, whatever the value is there in this buffer of out location, you have to put it into a variable called as next consume. So what is the value of out now? Out by default is 0, right? So out is 0 here. What is there in buffer of 0? Come and see here. The buffer of 0 contains the value 100. Now this 100 will be placed in next consumed variable. Okay. Then we'll perform this operation. Out is equal to out plus 1 mod buffer size. Okay. What is the value of out? Which is 0. 0 plus 1 mod 5. Buffer size is 5, right? Here it is there. So 0 plus 1 mod 5, that is 1 mod 5. The value is 1 here. Out value is 1. Then decrement the counter. This is equal to counter minus 1. What is the value of counter? By default it was 5. 5 minus 1, which is 4. Okay. We'll again go back to this while loop. Now check whether the counter value is 0. What is the counter value? It is 4. Whether 4 is equal to 0? No. Come here. Then check for buffer of out. What is the updated value of out? It is 1 here, right? You can see. So it is 1. So what is there in buffer of 1? What is there in this location? Come and see in this figure. So in the location here, buffer of 1, we have the value 200. Now this 200 will be placed in next consume. 100 is gone. Now the new value is 200. Then perform this operation. Out is equal to out plus 1. What is the value of out? That is 1. 1 plus 1 mod 5. 2 mod 5 is 2. Decrement the counter again. 4 minus 1, it is 3. Again, come back to this while loop. Check whether 3 is equal to 0. No. Come here. Now what is the out value? It is 2, right? So what is there in buffer of 2 location? This location, it is 300. So that 300 would be placed in the variable next consumed. Okay. So it is 300 now. Perform this operation. What is out value? 2. 2 plus 1, that is 3. 3 mod 5, which is again 3. Decrement the counter 3 minus 1, which is 2. Okay. Now again go back to this while loop. Check whether 2 is equal to 0, which is false. Then come and see the buffer of out. The latest value of out is 3. What do you have in this location 3? You have the value 400. That 400 will be placed in, sorry for this. Okay, 400 would be placed in the variable next consumed. Again perform this operation. What is the updated value of out? Which is 3. 3 plus 1, 4. 4 mod 5. You have 4. Okay. Then decrement the counter, which is 1. Come back here. 1 is equal to 0. No. Then the updated value of out is 4. So out of buffer of 4, you have value 500. Place that in your next consumed variable. Then out value is 4. 4 plus 1 is 5. 5 mod 5. The buffer size, 5 mod 5. You have 0. You have 0 over here. Fine. Then decrement the counter. It is also 0. Okay. So now check whether while counter is equal to 0. The counter value is 0. 0 is equal to 0, which is true. That means your consumer process, it stays in this while loop until your producer produces an item. Why? Because now this buffer is empty. Okay. Now let us look into the problem of this one. So in the producer process, we had a statement. In the producer, we had a statement counter plus plus, right? Now this can also be written as counter is equal to counter plus 1, right? Okay, so this, whenever in a system you are executing this type of instruction, we make use of the registers, right? So let us take register for this one. So whenever you want to perform this operation, counter plus plus, incrementing of the counter by 1. What you can do is like whatever the value of counter is there, you put into one register. For example, register 1. Then what you do? You have to increment it by 1, right? So register 1 plus the value 1. So whatever the new value is there, you put into the same register. Now whatever this register value is there, you again place back into the counter. Say suppose your counter value is 5. This 5 will be kept in your register 1. Okay, now your register 1 value is 5. So the next statement is register 1 is equal to register 1 plus 1. That means what is the register 1 value? It is 5, right? 5 plus 1, which is 6. So 6 now will be placed in this register 1. Okay. Next you have counter is equal to register 1. What is the register 1 value? Which is 6. Now the counter value, the same value would be placed in the counter variable. So this is simple statements, right? So here T0, T1, T4, they are nothing but instructions, okay? Like instruction 1, 2, 3, I have just given the name T0, T1, T4. Fine. So similarly, in the consumer process, we had a statement counter minus minus, right? So we had counter minus minus, that is nothing but counter is equal to counter minus 1. So how can we write that? So first move the counter value to register 2, then decrement this register value by 1 and put it into the same register. Then whatever the updated value of register 2 is there, place it into the counter. Again I have given some instruction numbers here, T2, T3, T5. Okay. And remember this counter value, counter variable, it is shared in between your producer and your consumer process. Now let's say this will execute these instructions one by one. Say suppose the order is that this is the order. Let's say T0, T1, T2, T3, T4, T5. So in this order, your instructions are getting executed. Now we'll see what will happen. First, T0 would be executed. We'll assume that counter value is 5. Okay, we'll assume counter value is 5 here. So the producer, what is T0? This is a producer process. This side, this is producer thing. Decrementation is your consumer thing. Okay, so T0 is in your producer. What does it do? Whatever the counter value is there, it will put into register 1. We have assumed the counter value is 5. So producer will execute this statement, register 1 is equal to counter. That means your register 1 now has the value 5. Okay. Next, T1 instruction is executed. That means again T1 is from your producer. It executes the instruction register 1 is equal to register 1 plus 1. So 5 plus 1, that is 6. So now your register 1 has the value 6. Now T2 instruction would be executed. Where is T2? It is in the consumer side, right? So what is T2 instruction? So this is statement register 2 is equal to counter. That means counter value is put into register 2. What was our counter value? It was 5, right? Previously. So see, you are updating till here, you are updating the register 1, but you are not updating the counter value. So after execution of these two instructions, you are directly jumping into this instruction. Okay, so that's why your counter value is still 5. Your consumer process still reads the counter value as 5. That's why in the register 2, you have the value 5. Next, T3 instruction is executed. It means what it does, it decrements the counter by 1, right? Register 2 by 1. So 5 minus 1, that is 4. That 4 would be placed in your register 2. So these two instructions have been executed, T2 and T3. Next, T4 instruction is executed, which is your producer side. Okay, what does it do? Whatever the value of register 1 is there, it would put into the counter. What was our register 1 value? Check the previous thing here, right? The register 1 value was 6. Now 6 will be placed in your counter, right? So counter value is 6 now. Then T5 instruction is executed. So which is your consumer instruction. What is it doing? Register 2 value is it is putting into the counter variable. What is your register 2 value here? It is 4. So now your counter value is 4. What should be the actual counter value? So it should be 5, right? Because maximum capacity of your buffer was 5, so the counter value was 5. So whenever you have executed the instruction in this manner, you have reached the inconsistency of data. This counter variable value is there, right? It is inconsistent. Why inconsistent? So in the producer process it is showing the counter value as 6. In the consumer process it is showing the value as 4. What should be the actual output? It should be 5. So let us say, suppose we'll exchange these two instructions and see if it makes any difference. No, right? Even if we exchange T4 and T5, the final output would be 4 and 6, right? So it would be 4 and 6 again, which is inconsistency. Now this condition we call it as race condition. Okay, we call this condition as race. So this race condition occurs whenever you have multiple processes, though that multiple processes that accesses the same shared data, or your, in our case it is counter variable, okay, simultaneously, and the instructions are not executed in a proper order. Okay, this race condition occurs whenever you have multiple processes that are accessing the same shared data simultaneously and the instructions are not executed in proper order. That time your race condition occurs. We are not executing the instruction in the proper order, right? Basically, what should we have done? So T0, T1, T4, then we should have executed T2, T3, T5. But we have, what we have done? After T0, T1, we have jumped here, T2, T3 has been executed, then T4 and T5 has been executed. So here the order of the execution has been changed. So with process synchronization, we can solve this race condition. So how can we solve this? Like at a time, either you execute the consumer process or you execute the producer process to access that shared variable counter. Okay, so this is some background on the synchronization. That's it for today. We'll conclude our session. Thank you.